In this module, we're looking at our first class of algebraic structures. They're called groups. We'll begin with a little bit of theory, and then after the theory, we'll look at lots of examples. So a group is a pair, G star, where G is a set, and star is a binary operation on G. So remember that means, among other things, that G is closed under star, right? Combining any two elements of G with the operation star has to give you an element of G. And here are the other three requirements for a pair like this to be a group. The operation has to be associative. We know what that means, but I have included the equation here. This is the equation saying that the operation star is associative. There has to be an identity element in G for the operation star. We know the meaning of identity element, sometimes called a neutral element. And here, as a reminder, is the property that has to hold for every element of G. E star A has to be equal to A star E has to be A. So item 2 requires that there be at least one identity, but as we know from our discussion on operations, there can be at most one identity. And knowing this will make the final of the requirements easier to state. So for every element little a in capital G, there has to be another element B in capital G for which A star B equals B star A equals the identity element of G. In other words, every element of capital G has to have an inverse relative to the operation star. So we have studied inverses in connection with our discussions of Z sub m and U sub m. So we have some idea of what that means. So one thing to note is that by item 2, which says there has to be a neutral or identity element, a group cannot be empty, cannot be the empty set. Okay, and now the notation for the inverse. So we'll assume that we have an element little a in capital G, and we have the other element little b, which, when multiplied by a using star, in either order gives you the identity. This is the element required by condition 3 in the definition. This is called the inverse of A. We knew that already. And we can argue using the group properties that every element has exactly one inverse. So item 3 in the definition says every element has to have at least one inverse. So what we would have to prove is that an element cannot have more than one inverse. So let's assume G star is a group with identity or neutral element E. And let's assume we have an element little a in capital G which has inverses B1 and B2. So we're assuming B1 and B2 are both inverses of A. And we want to argue that B1 has to be equal to B2. This is the normal way of showing that there's only one object of a certain kind. You assume there are two and show they have to be equal. So A star B1 has to be the identity because B1 is an inverse of A. So multiplying both sides of this equation by B2, we obtain this equation. And now, using the associative law on the left-hand side and the property of the identity on the right-hand side, we can group the B2 and the A together and multiply times B1 on the left-hand side. And E represents the neutral element, so E star B is B2 is B2. And since B2 is an inverse of A, B2 star A is the neutral element, is the identity element. So B2 star A is the identity. And now on the left-hand side, we use the property of the neutral or identity element once more. E star B1 is B1. So we have concluded that B1 equals B2. And you notice that the typographical error in the spelling of therefore has magically been fixed. So our notation for the identity element of a group. If the operation on the group is some kind of addition, the identity element E will usually be the number 0. If the operation is some kind of multiplication, then the identity element will usually be the number 1. And now our notation for the inverse of an element. So if we have a group and an element little a of that group, we will use one of the following notations for the inverse of A. A with a superscript -1. So this is read A inverse. And this is what we will use if the group operation is multiplication of some kind or composition of functions, or if we're just talking about an unspecified group with an operation star, we will use this notation for the inverse of an element A. If the group operation is some kind of addition, then we will use -A as our notation for the inverse of an element A. And now a little bit of shorthand, which I won't use very often, but which the book uses very frequently. If you have a set G and an operation star on G, and G comma star is a group, if it's clear from the context what the operation star is, then instead of saying the group G comma star, we may simply say the group G. So as I say, the book uses this shorthand very frequently. So one thing to keep in mind and to note is that a group does not have to satisfy the commutative property. Remember, the commutative property is that two elements can be combined in either order, giving the same result. So this does not have to happen in a group, but if it does, the group is called either an abelian group or a commutative group. These two phrases are used interchangeably. Okay, so why don't we look at a few examples. Which are the examples that we have looked at so far in the course are groups? Well, the integers with addition, the irrationals with addition, the reals with addition, Z6 with the operation plus sub 6 are all three groups. The positive rational numbers and the positive real numbers using the operation of multiplication. And here is a last example, U sub 6 using the operation times sub 6 are all examples of groups. Here are some non-groups. So why aren't these 5 sets and operations groups? Well, let's look at the natural numbers. These are the positive integers in 0 with the operation of addition. There is an identity element, and the operation plus is associative. The reason this is not a group is that not every element has an inverse. So, for example, the natural number 5 has no inverse in this group. The number that you would add to 5 to get the identity 0 is -5, but -5 is not an element of the natural numbers. And a similar thing is true for all five of these groups. Each has at least one element with no inverse. So, for example, if you take the integers with the operation of multiplication, this fourth example here, multiplication is associative, and there is an identity or neutral element for multiplication, namely the number 1. But there are elements of the integers that do not have inverses, which are integers. For example, 5. The inverse of 5, using the operation of multiplication, is 1/5, but that is not an integer. We will look at some of these examples in more detail in just a second. Okay, so what about the set of all functions from A into A, where A is some non-empty set, and this is the operation of composition. This is a operation that we talked about earlier. So will this be a group? The answer is no, as long as A has more than one element. As long as A has more than one element, A to the A, the set of all functions from A into A, under composition will not be a group, because there will be elements without inverses. We will look at that in a little bit more detail later. So let's take a closer look at some of the examples from the last couple of slides. I want to look at the example, find the identity element, and see how you calculate the inverse of an element. So these are all pretty straightforward examples. What if we take the real numbers and the operation of addition? The identity, if you're adding, the neutral element or identity is 0. The inverse of a real number, using the operation of addition, is -a. -a is what you add to A to get the neutral element 0. What if we take the positive reals using the operation of multiplication? So one thing to notice here is the positive reals do not have 0 as an element. That's important in order for this pair to be a group. The identity element, or neutral element, when you're multiplying, the identity element is 1. And the inverse of an element A, when you're using multiplication on the real numbers, is 1/A. Z15 with the operation plus sub 15. What is the neutral or identity element in Z15? 0. Almost always when you're doing some kind of an addition, the identity element will be 0. And how do you find the inverse of something in Z15? Well, you may recall that it's not as easy as simply taking minus a. You have to make sure that the inverse of an element from Z15 is actually in Z15. And recall, this is how we did it. The inverse of a is 0 if a is 0. Otherwise, you calculate the inverse by taking 15 minus a. And now let's look at U27 times sub 27. So remember, these are the integers between 1 and 26 inclusive, whose greatest common divisor with 27 is 1. The identity element, when you're doing some kind of a multiplication, the identity element will almost always be 1. And how do you calculate the inverse of an element of U27? Well, this is a little more complicated, but it's something we did do in our module on Z sub m and U sub m. So here's a brief review of the method. So since we know that we have an element of U27, we know that the greatest common divisor of 27 in that element is 1. And using Bézou's lemma, that means we can write 1 as a combination of 27 and this element a from U27. And then what we saw was that the inverse of a will be this number t mod 27. A inverse is t mod 27. So a quick example with numbers, if we want to find 7 inverse in U27 times sub 27, we first have to write 1 as a linear combination of 27 and 7. This we saw how to do when talking about Bézou's lemma. Right, we do it by repeatedly using the division algorithm and then working backwards. It was a little bit of a complex process. And so this 4 mod 27 should be the inverse of 7 in the group U27. So 7 inverse in U27 is 4 mod 27, and as we know, the remainder when you divide 4 by 27 is 4. So one way to describe a group is to give a table for the group operation. You may remember from elementary school seeing multiplication tables and addition tables for adding and multiplying ordinary numbers. Well, you can do the same thing in any group. So, for example, here is a table for a group G star, and the elements of G are 0, 1, 2, 3, 4, and 5. They form the column headings and the row headings. And then the operation is described here in the body of the table. So you probably know how this works. So for example, to calculate 2 star 5, you find the row whose row heading is 2. You move over to the column whose column heading is 5, and the entry in that position in the table is 2 star 5. According to this table, 2 star 5 is 1. We could calculate the star of any two elements of G using this table. For example, 3 star 2 would appear here, 3 star 2 is 5. This is actually the table for the group Z6 with the operation of plus sub 6. Something we've talked about and which appears on the in our textbook on page 27. I might just say that it's fairly easy but tedious to construct the table for a group if you know what the group is and what the operation is. On the other hand, if somebody just gives you a table, it can be pretty difficult to decide whether or not the operation described by the table gives you a group. Okay, and now a final example, at least for these slides. We're going to look at a group called sim of A. So we get sim of A from the set of all functions from A into A. Remember, the set of all functions from A into A is not a group. If you use the operation of composition, but we can get a group from the set of all functions from A into A by eliminating those elements that don't have inverses. The result will be this group which we're calling sim A. So remember that a function from a set to itself has an inverse if and only if it's one-to-one and onto A. And another fact that I am asking you to recall is that for a finite set A, if a function from A into A is either one-to-one or onto A, then it has to be both one-to-one and onto. But maybe an example would be better. So let's say that capital A is the finite set whose elements are the numbers 1, 2, 3, and 4. Okay, so I've just made up a function from A into A and written it in matrix notation here. So this is the function that sends 1 to 2, 2 to 4, 3 to 1, and 4 to 3. This is one-to-one and onto because each number in the set capital A appears exactly once in the bottom row. Right? The fact that every number appears at least once in the bottom row tells us that the function is onto. The fact that no number appears more than once tells us that it's one-to-one. Okay, a couple of definitions here. If you take any set, then a one-to-one function from A onto A, right, requiring both one-to-one and onto, is called a permutation of A. And if A is a finite set, then sim of A is shorthand for the set of all one-to-one functions from A onto A. Actually, this is also used for infinite sets, but we'll be dealing mainly with finite sets in this course. And now the theorem for any set A, that the pair sim A together with the operation of composition is a group. We'll leave the proof of this theorem for the exercises, and we will look at a few examples. One thing we have to note here is that sim of A is also denoted capital S sub A. Both these notations are used frequently, and it's the second one that is used mainly in our textbook. Okay, now a few examples. Suppose A is the set whose elements are 1, 2, 3, and 4. What is the identity element in the group sim A? Using the operation of composition, I should have said. Well, we know that the identity element, we know what the identity element in A to the A is. We've talked about this before, had a homework problem on this. It's the function e from A into A defined by e of x equals x for all x in A. So the identity element in A to the A, if A is the set 1, 2, 3, and 4, using matrix notation, we have seen before. It's the function that sends 1 to 1, 2 to 2, 3 to 3, and 4 to 4. So we know that the group, the set sim A, does contain an identity element. So let's just do a few sample calculations in sim of A. These are pretty similar to calculations we did earlier when we were discussing e to the A, so we won't spend too much time on these. So I just wanted to calculate F composed with G and G composed with F. So F composed with G, 1 to 3, 2 to 2, 3 to 4, and 4 to 1. And this is, I did exactly the calculation that we did earlier in the course. So we're doing G and F in succession. G is done first. So we consider the number 1. G sends 1 to 2, and now we apply F to 2. F sends 2 to the number 3. So the composition, the net effect of doing those two in succession is that 1 is sent to 3. The other 3 entries in the bottom row are found in a similar way, and G composed with F is found in a similar way. Okay, so now let's look at the problem of finding the inverse of an element of sim A. So in this example, A is the set consisting of the integers 1 through 4 again, and F is this permutation of the set capital A, right? I know it's a permutation because every element of capital A appears exactly once in the bottom row. And now I want to find F inverse. So here's the equation we're looking at. Here's what has to happen. If you multiply F inverse by F, the operation here is composition, you have to get the identity element. So I would like to fill in these 4 squares so that this permutation is actually F inverse. Well, let's see. Composing these two functions, 1 has to be sent to 1. F sends 1 to 2, so if the net effect is going to be that 1 is sent to 1, F inverse will have to send 2 to 1. The composition has to send 2 to 2. F sends 2 to 3, so F inverse is going to have to send 3 back to 2. And similarly for 3, the composition sends 3 to 3, f sends 3 to 1, so f inverse is going to have to send 1 back to 3, and 4 is going to have to be sent to 4 by f inverse. So essentially what we've done here to get f inverse is we've turned f upside down, and then we've rearranged the columns so that the numbers in the top row are in increasing order. I'm not sure that's the best way to look at it, but it is one way. And now some of the elementary properties of groups, a couple of which we already know about. So a theorem. If a G star is a group, there is exactly one identity element in G. This is something we proved before. If there's an identity element for an operation, there has to be exactly one. Every element of G has exactly one inverse. We proved that. And now the last three we have not proved, and these will appear in the exercises. Number 3 is the cancellation laws. If A times B equals A times C, then you can cancel the A. And similarly, if B times A equals C times A, you can cancel the A and get B times C. And one thing to note here is that I'm using the convention of writing AB as an abbreviation for A star B. This is something our book does pretty consistently. So it's probably a good idea to get used to it. Okay, and then 4 and 5 provide us with a couple of tools for showing that two elements are inverses of each other. If you multiply two elements of the group, A times B, remember this means A star B, and get the identity, then A has to be the inverse of B, and B has to be the inverse of A. And number 5 gives us a way of calculating the inverse of a product. Right? A star B inverse is B inverse A inverse, or B inverse star A inverse. So you get the inverse of a product by multiplying the inverses of the elements in reverse order. And finally, the inverse of A inverse is A. So all of these things are fairly easy to verify.